And the rate of reaction chapter in the workbooks is quite long. So what we're going to do in this video is just talk about the absolute key theory behind the factors that affect the rate of reaction. So we're going to skip past lots of boxes, but we're just going to cover the absolute basics, the crucial basics. So first things first, if we're going to explain rate of reaction, we have to know what two things must happen if a reaction is to occur. And those two things are as follows. Firstly, reacting particles must collide. And that collision must have enough energy. It must have enough energy to break the bonds of the reactants. The collision must have enough energy. So two things, particles must collide and the collision must have enough energy. Now, when we talk about factors that affect rate of reaction, we're going to talk about four: concentration, temperature, surface area, and catalyst. Now, those four factors will affect either the number of collisions, because particles must collide, or the energy of the collisions, because the collision must have enough energy. So taking one at a time now, we'll explain each in a little bit more detail as the video goes on, but concentration to start with. This concentration is for solutions. Okay, so this is for reactions involving solutions. Now, if you have a high concentration solution, you have a lot of particles in that solution, so you will increase the number of collisions. So if you increase the concentration, it will increase the rate of reaction because it will increase the number of collisions. Now, temperature. This affects every rate of reaction. If you heat a reaction up, it goes faster. If you cool a reaction down, it goes slower. Why? Well, if I'm honest, it's both of these. If you heat up particles, they move faster. If particles move faster, you get more collisions. But this is possibly the more important factor. If you heat the particles up, you give the particles more energy, so the collisions have more energy, and that's a more important factor. But we'll write down both here. Both number of collisions and energy of collisions. Next, surface area. This is for solid reactants. Okay, and we're talking about the number of surfaces on show. If there's more surfaces on show, then the surface area is greater, so there's a greater area over which collisions can occur. So again, it's number of collisions for this one. Number of collisions, not energy. By breaking a solid up, it does not increase the energy of the collisions, but it does increase the number of collisions. Last one, catalyst. A catalyst provides an alternative route by which the reaction can take place that requires less energy. So this is the energy of collisions. It means the collisions need less energy. So this is energy of collisions. Right, let's explain a little bit those in a bit more depth on the next few pages. As I say, there's lots of boxes here. We're not going to do all of them. Okay. We will have a quick look at this one. So we've got two acids here. What have I said? I've said presumably the same volume in each of these beakers. Okay, I've said this one contains 0.1 molar or 0.1. Let's change that to 0.1 mole per decimeter cubed. Okay, that's often the unit we talk about. So molar written like that could be moles per decimeter cubed. It is moles per decimeter cubed. And what I've said is just imagine that there's 5 acid particles in this beaker. Now, the reality is there's billions and billions of acid particles in this beaker. Okay, but this is 0.1 mole per decimeter cubed. And let's just say 0.1 mole per decimeter cubed has 5 acid particles. Well, this beaker over here on the right, we're saying is 0.5 mole per decimeter cubed acid. Well, if this had 5 particles, and that's 0.1 mole per decimeter cubed, and this is 0.5 mole per decimeter cubed, this is 5 times as concentrated as this. So if this had 5 particles, this would have to have 25 particles. So just while I'm drawing these 25 particles out, it's going to take me a while, isn't it? 4, 5, 6, 7, 8, and I'm drawing hydrogen ions here because hydrogen ions are, of course, the particle of acid. 10, 11, 12. what I want you to be thinking about is, in which of these beakers is there going to be more collisions? 14, 15, 16, 17, 18, 19, almost getting there, aren't we? 20, 21, 22, 23, 24, 25, right. In which of these beakers are we going to have more more collisions between acid particles and another reactant? And the answer is clearly this one. Why? Because there's a much greater concentration of particles. So, explain with particle theory why magnesium reacts faster in this beaker. So in other words, why does magnesium react faster in this beaker? Well, if we put magnesium in there, there's going to be loads of acid particles for it to collide with. If we put magnesium in here, there's not many acid particles for it to collide with. So, let's just do a quick flow chart to show this. Now you need to write these in sentences. I don't have that much time, so I'm not going to. I'm just going to say high concentration, okay, equals lots of particles, equals lots of collisions, equals fast rate of reaction. And that's what we mean by talking about particle theory, because we're talking about particles and how they affect the rate of reaction. High concentration of acid, there's lots of particles present. If there's lots of particles present, there's lots of collisions. If there's lots of collisions, there's a fast rate of reaction. And that's how concentration affects rate of reaction. Okay, next, temperature. Okay, so it says here, explain using particle theory why increasing the temperature speeds up the rate of reaction. Well, if we increase the temperature, okay, the particles have more energy. If they have more energy, they move quicker. And collide more often. If they move quicker and collide more often, the collisions have more energy. If the collisions have more energy and there are more collisions, then the rate of reaction will be faster. So, more collisions and collisions with a higher energy equals a faster rate of reaction. That's an absolutely crucial box, that one. Next factor, surface area. Again, I'm going to miss out lots of these boxes now. I'm just going to go to the absolute basics about how surface area affects rate. Now, the first thing to say is we get a greater surface area by having smaller particles. Okay, and that's what this diagram here shows. Here I've got 10 grams, a 10-gram lump, I've said, of calcium carbonate, a 10-gram cubed lump of calcium carbonate. Now if you look at this number of surfaces here, the surface on the front, one on the top, one on the side, one around the back, one on the bottom, and one there. So I've got 1, 2, 3, 4 around the back, 5 on the bottom, 6 there. I've got 6 surfaces on show, haven't I? Okay. Now most of the calcium carbonate particles are going to be inside that cube. If I put that calcium carbonate lump into acid, it will react with acid, but the acid particles will only be able to touch the surfaces. They will not be able to touch the particles inside until the ones on the surface have been reacted and worn away. Okay, so we can make this reaction faster by slicing it, say, straight down the middle, because then suddenly we'll have created extra surfaces that the acid can collide with. So, I mean, if we have, so for example, I've cut this in half down here now, and look, suddenly we've got a whole new surface there, and a whole new surface there, okay, that suddenly the acid can see. So we've now got extra surfaces that the acid can collide with. We've made 2 extra surfaces, 1, 2. So we've still got the 6, the forward, the side, the top, the back, the side, and the bottom, but we've suddenly got 2 extra surfaces there and there, so 8 surfaces. So by putting one cut, by making one big particle into 2 smaller particles, we get extra surfaces greater area for collisions to occur. Okay, that's true for every time we make it smaller. Every time we make this 10 grams smaller into smaller lumps, we get more surfaces because we expose more surface to the acid. So what we're going to say here, explain in your own words how we can increase the surface area of a solid. You increase the surface area by making the particles smaller. This means there is a greater area for collisions to occur. This increases the number of collisions which increases the rate of reaction. Increases the rate of reaction. Now the last factor we're going to talk about is catalyst. Now catalyst is a substance that if you add it to a reaction, it speeds the reaction up. So a substance that speeds up a reaction. And the way it does this is by providing an alternative route, that requires less energy, The catalyst itself, and this is important, the catalyst remains unchanged. So a nice simple little thing for you to think about here. Okay, about providing alternative energy. Let's say we've got these houses here. Okay, the shops for these houses is down here. So the people have to walk over the top of the hill and then down to the shop. Now that's going to take a long time to climb that hill. It's going to take a lot of energy to get up there. Okay, but just imagine what happens if we build a tunnel through the hill. Suddenly the people can walk through the tunnel, requires much less energy because they don't have to climb the top of the hill, so therefore they get to the shop much quicker. So the tunnel is like the catalyst. It provides an alternative route by which the reaction can take place. Okay, now we have energy level diagrams in chemistry. It looks surprisingly like the example we just looked at. So normally particles have to collide, and the collisions break the bonds of the reactants, and that requires, say, the energy from here to here. This is now a graph, energy on its axis. So the initial collisions, okay, for it to be successful has to be that from there to there, that much. However, if you add a catalyst, it provides an alternative route, and suddenly the collisions need less energy. Okay, so this is now an energy level diagram for a catalyst with a catalyst. The catalyst provides an alternative route by which the reaction can take place that requires less energy.